the fourth project needs to be submitted by the 26th of July. Okay? For all of you. But if there is something special, for example, you need to be on a flight of 3 days or something like that, or you have a good reason, so you can ask for an extension of 1 week. Okay? In very special cases, you can get even more. Okay, now regarding the grading, so this is project 4. So 1 week is the 2nd of August, or something like that. Okay. 1 week, yeah, it's a 2nd. Okay, so extension of 1 week. I'll be nice and add the weekend. So you can ask an extension until the 4th of August, but not all of you will be approved. Now, the grade will be different than what you see in the project itself. The grade will be based on 70% of presentation and 30% of the accuracy of all projects. What does that mean? A day after the 26th, meaning on the 27th, we will schedule meetings of 20 minutes each, in which you need to present one of the answers to your, the truth is that I had it in one of my courses, and then I said to Izar that this is what I want to do, and then he told me that he spoke with you about this day, maybe. So no, but really, it's not you. It's not you. It's something that we decided to do because you cannot study just by copying ChatGPT. I'm sorry. So this is the reason why we don't do it for project 3, because this is behind us. But for project 4, we want it to be useful for you towards the last quiz. 1 minute. Towards the last quiz. Therefore, you will have 70% presentation. So again, in this presentation, we tell you, each one of you, to present random question from your project, and you get a grade, not for your oral presentation and so on. We give you a grade for how well you understand the material. Okay, we won't read it with you. 1 minute, Sophie, sorry. Yeah, okay, sorry. So we won't give you a grade regarding how well you present and so on. We'll just really see that you understand what you wrote and what you were doing, so you can use ChatGPT, no problem. But you need to understand what you're doing. And the rest of the grade will be due to accuracy. Okay? Now, for this reason, we decided to keep it before the final quiz, because we want to help you in studying towards the quiz. Because starting with the project will be the best thing for you. Okay? So this is about how we are going to make it. And if you need extension, because some of you really do need extensions, then you need to fill in the Google form I've just sent and ask for this extension. Okay? Yes, sir. No, we open your solution together. Yes. Yes, we open with you the solution and we talk about it. We ask you to present it, to explain what you did.
And so, for example, because I know sometimes that some projects say, to be honest, I will try this and I go from say, this question is.
Yes. We won't reduce points if you feel that you were not sure about what you were doing and you tried something. This is not the aim of this presentation. The aim of this presentation, again, is to see whether you really studied from the project or did you just copy and paste ChatGPT. And we are not angry about you. This is not a punishment. It is really, really important for me to tell you that because I had it in one of my during the Corona time. This was the way that I had exams in my math courses, and this was the best way I ever had any grade. Okay, because I think that when you need to submit something and then you talk about it, it's not very hard. If you really studied, you have something to say, even if you were wrong, so you'll be reduced in the accuracy, okay? But you do know what you did. You really try to solve it, okay? So I think this is the best way, and these are most of the time these are even. I know that most of your grades are really good in the project, but now you will really know what you know about the subject because the current grades tells nothing about your comprehension. This is how I feel, okay? And it's not that they are very different from previous years. So it's common that the projects are very highly ranked. It's okay, but I want you to really, I don't know, to really take something from the course. You know, not just the title data scientist, but rather if it opened your appetite for further research in neuroscience, I think this is the best. And if not, if you want to go to the industry, I really want you to go to the industry and offer something and not just have this title. Because after people look at the CV and they give you questions during the industry interviews, and if they see that you really understand nothing about data science, they will just tell you, sorry, we don't believe this title. I don't know where did you do it and what kind of university, but this is, you cannot start working here. Okay? Yeah.
Not question one, right? Like it's like out of the random question?
No, also in question one and reading the paper.
Okay.
Yeah.
Because I thought it was going to be more about.
Yeah, you have a really very structured, it's about 3 paragraphs to read. That's it, I feel. Or maybe a short paper of 2 pages or 3 pages, the Shaw et al. From 1999, and you need to kind of understand it in a vague way. And another supplementary figure, and 1 paragraph for methods. So it's not that much when you think about it. Okay? Yeah, that's it. Only for project 4. What happened in the previous project is just irrelevant anymore. What happened. We say there is a phrase in Arabic that says, what happened is dead. Il fatmat. Okay? Yeah.
You get an extension, do you have to present the topic?
There. Like, I mean, like each one will have its own extension, and then we will have another day and we'll schedule it. But I highly recommend, really, really highly recommend that if possible, don't use this extension. First of all, get rid of this course, okay? Enough is enough.
Just if I have
And-
followed by the project deadlines.
Okay.
26, so I think I don't have.
Are there more students like this, or is it? Okay, no problem. So in such a case, of course, no problem for extension. But if possible, please try to finish it. And we can just schedule the presentation, although this is very short, it's 20 minutes, but we can schedule it like after the exam if it will be easier for you. Okay? Yes, Arthur.
No, I like this. I was worried about the deadline. I was thinking of the previous one.
Yeah,
It's one I-
it's almost 10 days from now. I think this should be enough. And if you, I'll tell you what, if you see that when you arrive the 25th, and this is just really impossible to submit, write an email and another day or something like that will be possible. But try now to submit by the 24th, okay? I'll tell you why. Because I want you to have enough time to prepare towards the exam, okay? Which is at the 31st, right? So try to submit it by the 24th. When is that then? Sorry? 30, yeah. So I really recommend that you have 3 days for the exam. So try to submit by the 24th. If it is really impossible, write a special request for extension. And so I recommend that you will try to submit it by the 24th. And then in the worst case, you can do it by the 26th. I think it is highly possible. Okay? And if you see that you didn't make it, then write a special request for extension. But again, if you try, and let's say, for example, there are, I don't remember, 3 or 4 questions, 4, and you really manage to finish only 3 out of them, you already acquired 3 questions that you really understand fully towards the exam. So we will give you an extension for the 4th one. It's okay. But this is for you, because otherwise what will happen is that you will just study for the exam and then you will start working on the project and it will take you 2 weeks to submit it. And the course will end by the end of August. Okay, so no, we want you to do the project before, to get rid of it, to make the most that is possible. Okay. And if you won't finish by the 26th of July all of the questions, it's okay. So just finish the first 3, then stop, have this extension for 1 week, finish the exam, finish the project, and really, let's finish with it. Okay? Yes. Yes, it will be a Zoom meeting. I probably, since there are many students, we will split it between Bench and me. Okay?
And it's not gonna be the following day, right? The following is.
Why not this 27th of July? Why won't you just? Oh, yeah, no, so it will be on Sunday. The what? We will publish so in the 28th, no, this is the exam. Okay, so it will be either on the 28th or the 29th.
And who has the exam on the 28th?
Yeah, and we will just send you the possible, is that okay? I think yes. So we'll just send you the possible slots, and then each one will choose the relevant slot for you. You can do it also face to face, yes. Yes, yes. You can choose. We will give you the possibility to choose if you prefer online or face to face. It's the same for us. Okay, great. Oh, I told you. Okay. I was a bit afraid from your comments, but I think it's really good. I think it's a great way. Yeah, it's much better for you because then you kind of know your final grade plus minus half point. So
And for OSNATs, like workshop class, that's what we had to do. So
Really?
it's not really that different. I think the people did in front of the class.
No, so this is the difference. I don't want you to do it in front
Oh,
of
you
the class.
did it just with those now?
I know this was another possibility. So first of all, it's a waste of time for me to ask you to present it in front of all the class. I don't think that you, after, I want to hear each one of you. Not that one of you tells everyone.
But for us, it was also just a professor. Like I did just with the professor, everybody just did. And
So-
you've done that before too, so I don't think it's that.
Right. I think this is the best way to evaluate the project. Okay? And again, it's not a punishment. It's really important for you to understand. Okay. Great. So Sophie, you help me in writing this in the WhatsApp Discord and make sure that everyone knows that. Great. Okay. So why am I on filters? This was not supposed to, oh, sorry, it's this one. So we were speaking about cross correlation, and now I want to show a bit of the ways to use spectral analysis in neuroscience. So first of all, over here, these are the equations of a power spectrum, okay, which is something that you already know. Power spectrum diagram, in which you have the relation between the power of specific frequency, and this is given in decibels per hertz. And the reason for this unit is concluded by the Parseval theorem. Again, a lot of very theoretical math, not that important. I'm just reminding you, what does a power spectrum mean? Now, what we know that, for example, when we are studying audio stimuli, we know that our voice or singing and so on uses a lot of frequencies of speaking. And now we want to understand how to present the change in frequencies. And this is something new that is called a spectrogram. Okay, so here you can see a spectrogram of a speech. This is probably the way that you know the signal of voice coming, you know it from all the equalizer and so on. So this is how the signal of voice looks like. This is the fluctuations of the air. And then when we want to plot the spectrogram, we create something like this. So over here, we can see time, and we can see the frequencies. So the x-axis is for time, the y-axis is for the frequency, and the color bar for the power. So you can see, for example, at the first half minute, that most of the highest frequencies were around 1,000 or 2,000. Later on, this frequency changed over here after after open quasar. It changed to higher frequencies of 30,000 and 40,000 hertz. Okay, so you can see here the changes within time. So now we want to understand how to create such a spectrogram, because now we don't take the full signal and perform a Fourier transform for all of it. We want to perform a Fourier transform only to part of the signal, to small parts of the signal. So maybe here it's another way to explain the differences. So over here on the left, we can see a stationary signal that we have these three frequencies together. And when they are summed up, this is the power spectrum of the frequency over here, that we can see a delta function of 1, 5, and 8, right? But now we can see a time variant signal, so that the 1 hertz frequency didn't begin right at the beginning, it took it some time to begin this fluctuation. And the 5 hertz began later, and the 8 even later. And then when you sum all of them up, you can see that the frequencies are summing more and more dense, the more you get into the rest of the signal. So a spectrogram should look like this, right? So that at the band of the 1 hertz, the lower band, it starts over here and it stays for all along the signal. And for the 5, it begins later at the same time, and then the X over here. Is that clear? So that you can see again, the idea of this delta function is represented by the fact that we have here this red dot, the very strong one, and I don't want to say this is the delta function because it is not. It's across time a stable frequency. Right. And over here we can see an example for a raw signal, which is of course much more complicated. So the truth is that when we're doing such a thing, we have a problem. Since what we are performing, we are taking part of the signal, not really clear over here, sorry. So when I explained it as if what we're doing to create this spectral is that we take part of the signal, this part, we perform for it the Fourier transform. And then we can take the next bit, perform for this one, the Fourier transform. What is the problem with such an amplitude? There are a few problems, but one of them is one that you should already know. Yes. Yeah, this is like a bit more complicated, right? So this is what is done. Talking about wavelengths today, right? So I want to speak about something in relation to filters. When I say that I take this part and perform this one Fourier transform, it's like filtering the rest of the signal. It's like multiplying this part by a rectangle. So when I perform the Fourier transform, I will have ripples, right? So I'm going to have irrelevant frequencies only due to the fact that I have this edge effect. So how would you offer to solve such a problem? Yes. To change the filter that we're using, or again, what, did you say to change the filter? But then, I don't know if you remember, we saw that if you apply a filter from the frequency, it creates ripples in time domain. So you're just adding ripples over ripples. You cannot win math. So what other possibilities? So yes.
Try to use a smooth, but then you expand your limit.
Exactly. So you will pay a price in the time resolution for that. So another possibility that was offered is to average, to take a moving thing like a convolution on one, and for each bit perform the Fourier transform. And when they are overlapping, you average across them. And then when you average, this takes really down the ripples. Okay? This method is called the Bartlett. Okay? And the last one, which is nowadays the most common one. Okay, so here is an example for Bartlett. So we can see over here the spectral density, and this is what we want to see theoretically, but still we have these ripples over here. You see this added frequency and this noise over here. And here are the normalized residuals when you subtract them. And this is what happens in Welsh. And you can see that Welsh has even higher residuals. So a new method that is commonly now used is called the multi-tapper. And this kind of method, we're doing the the following. So we are taking the data, and we are using different filters on this data, very similar to the idea of wavelength. And then for each one, when we are filtering, we are performing this fast Fourier transform. Therefore, for each bin, we are taking different shapes of peppers. And these peppers, you can see that they have like a kind of this inner frequency in them, right? So this is 1, this is 2, this is 2, this is 1.5, and so on. And then when you have this filtered data, you perform the Fourier transform, and you average across these different types of filters, and you get this multi-tapper spectrum. So you can see here, for example, this really nice idea that if we use only the Bartlett, this is how the spectrograph looks like, very noisy due to these ripples that we have. Here we use the Welsh. So in the Welsh, we just take each bit separately, but here this is how the multi-tapper looks like. So the multi-tapper has two advantages. First of all, in regard to the ripples, and the second one, it is due to the trade-off that you were talking today with Izar, right? So this is this trade-off. I really like this one. So that in your signal, you might have different frequencies, right? And the resolution to sample each one of them might be different. So the idea behind multi-tapper is that the convolutional window with the most relevant frequency for this type of signal will use the high frequency, while the one with the lower will be most influential. The convolution window with the lower frequency will be most influential in relation to this tolerance. Okay, so it's like using filters to find the specific relevant frequency.
You said the second one is lower, but lower.
Lower frequency. You can see that it's less dense. Okay, so let's try to have a nice exercise about that, and you have also the solution over here. So maybe someone would like to read and explain the answers. Let's start with read. Who would like to read? Yes, answer.
The exercise, right?
Yes.
If you use the Welsh or Bartlett window, what window size will you pick for a signal with sampling rate fs to achieve the following spectral resolution? A, 1 Hz using Bartlett window. B, 0.5 Hz using Welsh window with overlap of 50%. And C, 2 Hz using Welsh window with overlap of 50%.
Great. So please explain, first of all, what are the differences between the Bartlett and the Welsh? Which one is one? Do you remember? Yes. Yes.
Wasn't it the Bartlett movie window? And,
Yes.
The Welsh is.
No,
Yeah, it's-
exactly. Okay. So what does that mean? Window side to following spectral resolution. What does that mean?
We want to be able to distinguish frequencies up to, for example, 1 Hz.
Exactly. Okay, so this means that when we use the Bartlett window, we want to be able to differentiate between 2 Hz, 3 Hz, 4 Hz. This is the different sizes. Now, let's see why is the answer same as Fs. What does the frequency represent? The Fs represent. Yes. Great. And why do we care about it? Exactly. And why do we care about the Nyquist? So it's not about the problem of aliasing, but let's say that we have the frequency of 10. So our Nyquist frequency is 5, right? So if you want to have a resolution of 1 Hertz, this means that I want to be able to see the differences between -5, -4, -3, and so on, with jumps of exactly 1 between each one until 5. So why do we need to take the window size of fs, 10 samples? Why would that help us?
Those are frequencies, fine.
Yes. If we take 10 samples, right, then what frequencies can I get? Did you understand the idea of this Welsh window? It's taking the signal and just cropping bins of it. And we're asking what should be the size of such bin. Okay. So the bar rate is just the same as the Welsh, but a moving one. So the idea of the resolution is about the same. So why is it the same of fx if we want to have 1 Hertz resolution? It's okay, I want you to think. Yes.
So we want to capture a pattern that has a period of 1 second. So
Exactly.
1 Hertz means 1 period. 1 second. So if we want to be able to capture that entire period, we need a window that's 1 second long, which means we need to set as many samples as there are in this. The numbers equal to fs.
Right. So what Austin is saying is that he says, let's look at the lower frequency that we want to look at. The lower one is of 1 Hertz, right? 1 Hertz means that within 1 second, we have 1 cycle. Now, since our frequency is of sampling frequency is of 10 Hertz, this means that we have a sampling within every 100 milliseconds. You don't see that. We have a sampling within every 100 milliseconds, right? Is that so?
No.
Why not? Okay, so I'm saying that if our sampling frequency is 10 Hertz, then we have a sampling of this frequency every 100 milliseconds, right? And we want to capture it. So if we want to get this full cycle to capture it, we need all of the samples. Did you understand the idea? So this is why we use the same size as fs.
That's specifically because it's 1 Hertz.
Excuse me?
That's specifically because it's 1 Hertz.
That's specifically because it's 1 Hertz, exactly.
If it were,
So you're looking at the, now let's look at the one of 2 Hertz. Right, so 2 Hertz means that how many cycles I have within 1 second? 2. So this will look like this. So to capture this frequency, the lowest one, I need this size of window, which is half of my frequency sampling. And if I want to capture half hertz, which is the lowest frequency, then I want to capture this, right? To capture a full cycle of this one, I need 2 of the sampling frequency. Okay? So I'm looking at what size of window will give me a full cycle of the smallest frequency that I want in my spectrogram. Okay? So this was a nice exercise. Yeah.
Are these methods really not able to capture frequency from half a cycle?
Are the full one?
Yeah, for example, if you had half a hertz, is half of the cycle not sufficient to capture the presence of that frequency?
So let's think. So now I want to think about that you want to have a resolution that you have a difference between this one and this one, right?
Like half a hertz within one step. I'm
Yes.
looking at it only 1 second.
Yes. So you're saying that when I'm looking only at 1 second, will it be? Of course it will, right? Because it is lower than the Nyquist. But you're asking yourself whether you will be able to determine the differences between 4.5 and 5. Now we're looking again at the highest. And if you have only this size, 4.5 will just finish in the middle, right?
Yeah.
And 5 will have full cycles. So if you have just this size, you can't know the rest of the frequency. I think this is the because you're capturing for 4.5 and for 5, you're capturing the same number of samples, right?
For that's the actually rate of 10.
So for
That's what you're referring to?
I'm saying that now I'm looking at the highest possible frequency,
Yeah.
the 5. So to have the 5, this means that we have a fluctuation like this, right? There is, no, this was too fast, I'm sorry. So there's a drop here, height, and another drop here, and the height here, and so on, right? So you get just a peak and a trough, a peak and a trough, a peak and a trough. Now, if you have 5 cycles like this, you have 5 peaks and 5 troughs, right? This is the frequency of 5. I'm looking at the Nyquist frequency.
Okay.
And if you have 4.5, you have the same number of peaks and troughs. So you cannot distinguish between the two. So you need to have a full cycle.
Why does that, so again, why does that relate to whether or not you can detect that there's a frequency less than 1 hertz when our window is 1 second?
No, it's not about the size of the frequency that you're looking to, it's the resolution. You want to be able to distinguish between 4.5 and 5. To be able to distinguish between half and 1. Right?
So because we can't distinguish half frequencies of the other,
Exactly. Yes.
we won't assume. we
Yes.
distinguish it.
But this is just about the same as thinking what is the lowest frequency that we want to capture a full size of it. And this one is the answer for what is the size of the window. Okay? Okay, you can try to understand it again, and when you study towards the quiz, and we can talk about it again. It's okay. You saw that this course is kind of spiral. Sometimes you understand things not at the first time that you see.
But then when you put in the sampling frequency, it was just random, right? Because we didn't have a number.
Because, excuse me?
In the exercise, we didn't have a number to write in the sampling frequency. It was just
Yes.
random.
Yes, I was just giving an American example. Okay, so okay, yes. I'm looking. Let's double check. I remember that the Welsh is a non-overlapping one. Well, Bartlett, oh, sorry. It's the opposite. Bartlett is the non-overlapping and Welsh is the overlapping. Sorry for that. The Welsh, they are just the complementary to each other, and it's the opposite of what I said. So Welsh is the moving one, and Bartlett is the non-overlapping.
Like, is that, does it impact the window size at all, or is it just?
It's the kind of window. In this Bartlett window, you have non-overlapping windows, and each one you perform this Fourier transform. So this creates quite a lot of windows. But the Welsh, which is the one who has this moving window, since you're averaging across them, you have much less ripples. So they are lower down.
But with respect to spectral resolution, there's not.
So maybe let's try to look at this again. Okay. So we have over here, this is a spectrogram. So our x-axis is the time. The y-axis are the frequencies, and we want to know what is the size of each dot. Before you saw it like, I'll show it again. Over here, when I was talking about the spectrogram, right? It looks like the sizes of each one of these squares is equal. But practically, you can use different sizes. You can say that for the higher frequency, you want a less resolution in the higher window and smaller resolution in the lower window. Okay, and this is what you see here. So you can see over here that when I'm looking at the signal, this one has a high frequency. A high frequency over here, since I'm taking a smaller time window, has a lower resolution over here. I cannot distinguish well between 5,000 and 4,500. Okay?
In frequency, right?
In frequency. But over here, I take long range of time. Since the frequency over here is lower, then the resolution is much better over here. I can distinguish better between 10 and 5. Then I distinguish between 110 and 100. But I pay the cost by the time resolution. I have to take a longer one. So this means that our size of the time window is determined by the frequency that we have over here. And the smaller it is, then the bigger the size of the window. Yes.
So we were confused about whether the Bartlett or the Welsh was the sliding or moving one.
Yeah,
And yet at no point during our solution did it matter
right.
that one was a Welsh or one was a Bartlett.
Because this is because both of them are just squares.
Yeah.
So it doesn't matter this basic resolution. The problem is the same either for Bartlett or for Welsh.
So if we had 2 hertz using Bartlett window, it would
Yeah.
still be half of SS. It
Exactly.
doesn't matter that it was the Welsh window.
Exactly.
Okay,
Great.
is that right? Okay.
Great note. Okay, so over here, I'm trying to remember, is this one? Yeah, so there is a question over here, for example, from an exam about the resolution of the waveform. So we have the EG of a golden unicorn that is made up of three frequencies of 7, 18, and 100 hertz. So we know the frequency. And the amplitude of each component is 10 microvolts. Right? So this is, now we can sketch to ourselves the power spectrum, this signal. And where do we expect to see delta functions?
7.
Right, but it is highly dependent on our sampling rate. So over here, the waveform is sampled at 150 samples per second, and for 1 second. So we have also the size of the sampling. Sketch and explain the power spectrum of the EEG, and what should you write in the X and Y axis? What is the X scale resolution? And what is the maximum frequency? Let's try to solve it together. So we know that we have this power spectrum, and if we had a good sampling rate, then it would have been 7, 18, and 100. But our frequency is sampled at 150 samples per second, 150 hertz. Therefore, the Nyquist frequency is 75. So we don't see the 100, we see until 75, right? And now, due to that, we have an aliasing of the 100 to, you can see here in the answer, to 50, right? So instead of 100, we'll have this imaginary frequency here on 50 hertz. So this is the spectrum, and we know that the frequencies of the x-axis are, the x-axis is frequency, and the y-axis is voltage. We can have voltage, or let's have the microvolt. And we know that all of them are what height? 10. Okay, please, if you didn't follow, ask in the end. Try to listen up. And now we have a question about the resolution of the X scale. So what are the differences if I would have here all the possible ticks? This one, this one, this one, this one, this one. What is the size of each one? Why is it 1 divided by 150? So we have here, the waveform is sampled with 150 for 1 second. So you're saying since this is 1 second,
The sampling rate.
the sampling rate is 150.
Yes, that's one actually, yes.
So let's look at it. So we are saying that we have a waveform of 150 samples for 1 second. So the size of the signal is 1 second. How many samples do we have of the signals? What is the number of samples? This is the size, the distance between the samples. But if I have 150 samples per second, so how many samples I have in 1 second? N of samples is 150, and the frequency is 150. So the window size is 150. Therefore, the resolution is of 1 hertz.
Wait,
Yes. Let's have another example, okay? Let's say that I took my signal and I calculated the Fourier transform for the first 500 milliseconds and another Fourier transform for the other. Is that clear? So I have this really lousy signal like this. And this is for 1 second. And instead of taking off the signal, I had this Fourier transform for the first 500 milliseconds, and here for the second 500 milliseconds. Yes. So what is the resolution of mine? Now, I took only half of the samples. So what is the resolution? I'll show you again the previous exercise so you can try to find the relation. So if I want to achieve half of hertz, I take twice. But if I want to achieve 2 hertz, I take half of it. So this time, would it be this one or this one? The half or the 2 hertz? Did I take half of the sampling of the number of samplings or all of them? Half. So it's this one. Therefore, my resolution is down to 2 hertz. Okay, so if you have a better resolution over here, you pay the same size in the frequency resolution. So now instead of 1, was the answer to the previous question. Now, when I use this type of method, I have the resolution of 2. Okay, more clear now? I know this is confusing. Okay. Do you need a short break before we talk about cross spectrum and coherence? Have a 5 minutes break. I'll go on with this subject at the hour of 3 and 5 minutes. Show, excuse me, what to show? The previous exercise? This one? Yes. Okay. I'll also double check something on my phone. Yeah. You don't need a break, by the way?
Let's not
The-
move on yet.
Okay, so let's first finish with the question. Sorry. So, okay. You can ask questions, but I really wanted to have the break. So,
For you?
no, for you. You look,
One can be.
you look really exhausted. Oh, you.
No, it's just.
You don't get it. Okay, so look over here.
I think the moment.
So let's see this, okay? Do you understand? Please explain to me this law.
I don't think so.
Right. You're a very smart woman. Try to explain. What are the differences between these two rectangles? You can see here. Please write down.
I and E. Oh,
What does that mean?
I can see that the waves.
Yes.
That will have a difference. But seems to have the same.
Right. And yes, tell me more. You were right.
I see that there is.
Which one is more dense?
Then I would say.
Right. And what does dense mean in words? Higher frequency. Right. So to capture this higher frequency, to have this full wave, for example, I need to have a narrower window of entanglement, right? So let's say I take this one over here. Do I capture the full wave? It is harder to capture it. So over here we see that we don't need a lot of time to see specific, right? But that means that if we have this one, then we won't have a lot of a good resolution over here in the frequency domain.
We won't, right?
Right, because my ability to differentiate between this one and a bit more faster one is not very good, right? Do you see why? So if I have this signal, okay, and I take only this size to see this.
Yeah.
And now I take something which is just a bit more faster. It is hard for me to differentiate between them because here I have 2 peaks and here I have 2 peaks. So this might look as the same frequency for me. So for this reason, my resolution in the frequency domain is less good. The smaller I take, the time. Okay? But over here, I take a longer sample. And this kind of sample, I can catch the lower frequency. And when I catch this lower frequency, then it's really easy for me, since I took a long time, it's easier for me to see the difference between. So I have this one, and it is easier to see the difference between this one and this one, right? Because I took a lot of time. If I would take only half of it, it would be harder, right? I took only half of it in the time domain. So in the frequency domain, I paid my price. So this is what we see here. Is that not clear now? By the way, that we're talking about the size of the window in the higher frequency and so on.
Yeah.
So the last one we see better frequency resolution with less temporal resolution.
Yes. This is the main conclusion about it. Okay? You lost your nice break. I'm sorry. You decided to stay. But are you really open to go on? It's not that long. Now I think it's a bit more, it's not easy calculations, but the idea is more simple. Okay, so the last thing that we're going to talk about, I don't know if you've seen that during this pretty mathematical course, we were talking a lot about ways to show correlation between signals, okay? Because in neuroscience, this is one of the main questions that we're talking about. What is the relation between 2 signals? Are they synchronized? And how can we measure this synchronization? And this is something very unique to neuroscience. This is not commonly used for data science in the industry. For example, we're not interested in whether there is a correlation between Facebook profiles. For example, this is not one of the main questions that we're asking, but sometimes it is really useful to look at signals and ask yourself, are they driven by the same source? Do they have any relation between them? So I want to remind you that during the course, we were talking about mutual information, which is a way to consider relation between 2 signals by the probabilities that are inherent in this type of signals. For example, the firing rate. And we were talking about cross correlation, right? And also a bit about Pearson correlation, which is an easy version of the other correlations. And now we talk about the last synchronization method that is called coherence and phase locking. And this is in the field that is called cross spectrum, the relation between spectra of 2 different signals. So what we see over here, that let's say that we have two signals, and we want to see whether they have the same frequency, the same main frequency. So for example, we have these signals of X and this signal of Y. They both have about the same frequencies, right? So when we look at their power spectrum, one of them has a high power. Maybe it's not good for this example, but let's say that we have the two following signals. One of them looks like this, and the other one is very similar, but much lower. It looks like this, okay? So when we look at it, let's say this is 1 second. So what is the frequency over here? This is 1.5 hertz, right? Because we have a full period and then half period. So this is 1.5 hertz. Now let's say, for example, that when we have this frequency, we can assume that there is a relation between this signal and this one. Now, if we perform a Pearson correlation, what will be the relation between them? -1, they will look anti-correlated. Yes, there might be that they are correlated, just phase shifted to each other, right? And we want to have another way to calculate. So this one has an amplitude of 10, and this one has an amplitude of 1. So one of the possibilities to do is to create the spectrum of each one of them, and the spectrum of this wave is the delta function, very high delta function. Okay? And the spectrum of this one is the lower one. Now, a cross spectrum, what it does, it just multiplies them one by the other. And then it might be, for example, that if they have that the calculation will be highly deviated by the higher frequency of one of them. Okay? Right? Do you understand what I mean? So let's look at two possible cross spectra. So this is not of the signal. So we have a cross spectra of 1, that this is 1 and 5. And in this one, this is 1 and 3. Are they similar? Not really, right? Like they don't have the same frequencies, but since they have something that matches within 1, it will look like they're highly correlated at 1 hertz. But this is noise. This is not what we're looking for. We're looking at these signals. So we want to normalize the relation between the spectra by the size, the height, the amplitude of each signal, right? So that we can see the relation between these two. And this is what we see here. This is called the coherence. So what the coherence is doing, so I forgot to show, the S is just the multiplication of the two spectra and an average. And here what we are doing is that we are dividing by the spectrum of each of the signals. So this is normalizing to the amplitude of each one. And by this, coherence moves between 0 and 1. So coherence might be a measurement to show us the relation between two signals that are connected to each other, but might be phase shifted. So here is an example that we have this signal over here. And this is a ring signal of 10 hertz. And here we have white noise. Do you remember what does white noise means? That we have all the possible frequencies. Do you remember that? Great. And when we perform the cross spectrum density, since the white noise has all of the frequencies, this will look like there is frequency at 10 hertz. But when we perform the coherence, we can see that this is just noise And this is lower than the chance level. Okay? The chance level is computed by statistical tools of permutation tests and so on. But the basic idea is that when you divide by the size of each spectrum, you normalize the relation between them, and then you can see real relation between the signals.
Then how much will it cost the prospect?
You cannot. This is the reason why we don't use it. So what we do use? We use the coherence. So over here you can see two signals, and these signals are phase shifted between each other. And when you perform the cross-spectrum density, you can see here this peak. But the coherence, in the coherence, you can see that the coherence is 1. Okay? It's a flat line, yes.
And we want the level, the trust level.
This means that for the x-axis is for frequency in the coherence, and the y-axis is the frequency. So this means that for all the frequencies, they act the same way for the two signals. This is what coherence means.
Based on the.
Yeah.
One line, say,
Yes.
and then the next one, you don't see.
Ah, so over here, this is 1. Yes. Yes, it's because of the scale. Very, very low. But over here, the idea that when you see these peaks, you might say, oh, but there is a relation and this one and this one. And then, first of all, you use the permutation test, and you see it's not significant in comparison to Shapwa. And another thing, this just might mean, here when you see this peak, this might mean that there is a specific frequency over here that is unrepresented by the frequencies over here. So this is what it means. Okay? So let's have an example. In coherence, most of the examples in test are mainly comprehensions. I didn't see almost at all like real arithmetical calculations. Maybe sometimes there is something that is, I don't know, a coding of the idea, but we commonly use built-in functions. So you should ask Izar if he allows you to use the built-in. I believe so. SciPy should have it. SciPy no more?
Say, it's like, yes.
Ah, so very high chance that in SciPy they have it. Also, probably in NumPy. This is a very, very common. Yeah. Okay, so we have these two signals. Signal A is A sine 25t plus alpha, and B is B sine 25t plus beta. So, is there a relation between the signals? Yes. They have the same frequency, but what is the difference? Alpha and beta, which means different phases. So, the coherence between the two signals at 10 Hertz is, let's try to solve it. Should there be a coherence at 10 Hertz of the two signals? Do they act the same way at 10 Hertz? At 20, it is clear that they act the same way. So no, it's in the idea about coherence that it is independent of the phase. So even if the phases are not aligned to each other, the way each of the spectrum acts in each of these spectra is the same. So both of them at 10 have 0. So the coherence at 10 is 1. The spectrum of this signal, the spectrum of A and the spectrum of B looks the same. There is a delta function. Oh, it might be A or B at 20 Hertz. But at 10, right, both of them equal 0. There is no frequency of 10, therefore they act the same way at 10. So the coherence should be 1. Okay, so, and what size should it be? So first of all, we know that it's independent on the phase. This is the idea behind coherence. It doesn't look at the phase, only at the spectra, only at the color. So it's either C or B. Now the question is about the amplitude. So the amplitude of the coherence. This is the question of the amplitude is for comparison between coherence and cross-spectral. In cross-spectral, do we have dependency on the amplitudes?
Yes.
Right, and coherence? No, great. So the idea here is to answer D. So the amplitude does not depend on A and B, and the phase does not depend on alpha. Okay?
So wouldn't it mean that the phase does depend on alpha and beta, and the amplitude does depend on A and B, but the coherence does not?
The coherence, okay, so if it was a question about cross-spectral, then answer C was the right one. Because the amplitude depends on both of them. Because you just see what is the height and you see that they are kind of related to each other since both of them have, like here, in the cross-spectral, you see for both of them the same frequency at 1 with different heights. Okay?
But are we talking about the amplitude signal or the amplitude?
The amplitude of the coherence. The height of the coherence function. So it doesn't depend on amplitude coherence, neither on phase. Okay? And you have a project question about calculated coherence, and the last thing that you will do in the project is calculating something that is called phase locking. So over here you can see so far we were just talking all the time about the frequency, but we are also interested sometimes, we're interested on the phases. And over here, what you can see is an idea for phase locking. So for example, I think that I showed you it before when I started in the last presentation, that I said that sometimes these waves carry some information on the system, on the brain system, in relation to how excited it is, how much does it tend to converge to relation between these waves and these spikes. By the way, this is an open question in neuroscience. What does these waves represent? Nobody really knows. But we can see over here that there is a theory that says maybe these waves mean something about the probability to have a spike. So let's try to see if there is a relation between a specific band, specific filter, and specific spike. So if there is a high phase locking at the same peak, or please note, at the same trough, or specifically at the same phase, there would be more commonly a spike. So you can see over here that this distribution is very narrow. But another possibility is that there is a low phase locking, and the spikes can occur at whatever time, unrelated to whether there was a peak, a trough, or in between, at what phase I am. And we want to quantify these differences. So how do we do it? We won't go into too much details, but when we talk about Fourier transform, we learned that Fourier transform takes the signal and finds the frequencies. The transform to find the phase is called the Hilbert transform. And when you use Hilbert transform, you can see what is the phase of the signal at a very specific moment. So I can take the indices of the spike, look at the signal, and see what is the exact phase of this signal at the time of the spikes. And then I have for each spike its relevant phase, right? And I can see whether this is a narrow one or a wide one. And how do we do it? We take the signal, we filter it to different types of bands. Okay, this is also what we will do in your project. You will need to filter your signal to the most dominant band. You will see what is the spectrum of the signal. Then you will, for example, find out that 5 hertz is the most dominant frequency. So you will filter your signal. After you filter your signal, you perform this Hilbert transform and you see whether the frequency of the signal, the phase of the signal, is connected to the phase. And the last thing that you will need to calculate is what is called the preferred phase. And how do we do that? The preferred phase is not the most probable phase over here. What we are doing to calculate the preferred phase, okay, let's have a numerical example. So let's say that we had the following angles: 45, 90, 47, 77, and 87. So the preferred phase is computed as the following. It's like the time of this average phase, the average angle, but we do it a bit differently. So we create a vector with an angle of each one, so that 45 will be this vector, size of 1, angle of 45. 90 will be this vector with 90. 47 will be, I don't know, let's have dots. This vector over here, okay? So we take the angles and we create angles, we create vectors with these angles, size of 1. And now what we are doing, we are performing a vector sum. We are summing the vectors all together. This will result a sum, for example, over here with that we know and now we can calculate this angle. And this angle is called the preferred angle. This is like the average angle. And this is different, 1 minute. This is different than just calculating the mean of all of them. Because let's say, for example, that if you have we'll have 330 degrees. So this is like this vector, right? So if you put them like this is like averaging across the vectors only over here. But the contribution of this vector is more closely over here. So when you're using vector sum, you are getting away from the problem of the fact that angles are from a circle. Okay? So I know I didn't perform too many examples here at this stage of the recitation, but first of all, you have it in the project, so you will be able to understand it better when you write it, when you code it. And also in exams, it is not commonly asked like in an analytical questions, because performing all this Fourier transform calculation and of course Hilbert transform is it's impossible. Okay? Yeah.
I'm not sure, but if when we do the Fourier transformation, like with the complex sine wave, we get like the dots at the unity circle.
Yes.
And then we have like the difference the distance from the origin to the dot, and this is like our amplitude for the spectral,
Yes,
and the angle
it is exactly. This is what the Hilbert transform is performing. Yes, you were. It takes the angle. Great understanding. Okay. More questions? Yes.
I didn't get how we sum all the vectors, because
So a sum of the vectors is that we take the x's, sorry, the x's of each vector, so it's this one plus this one plus this one plus this one. We sum them up together and we take all of the y's, which is this one plus this one and this one and this one. And we sum them. And this is called a vectorial sum. But I can send you some video links about that. Maybe it is not fully clear for those who didn't study it in linear algebra, okay? And it is okay. You were not expected. Excuse me? This is called, there are two ways to sum vectors. One of them, maybe you remember from linear algebra, that you copy this vector and then you create like a long line and you take the beginning and the end. And another way is just taking the x values and the y values, summing them together, and this is about the same. Okay? What about this is just exactly the same as summing a vector. Great. Guys, I really want to thank you. I know it's been a very, very hard semester, also due to the war and also due to the fact that this is a very hard course with a lot of load. And first of all, I really hope that I gave you some of the pleasure of doing neuroscience with this type of tools. I felt that every time that I see you in one of the lectures and I start talking with you, it's like your eyes are open and you start to really understand new things. And this was what this course is for me, to help you acquire a bit some of the language of neuroscience. And I really believe that after you do it, you really understand much better neuroscience and you can do really complicated things, not only in neuroscience, also in the industry. So I really hope you enjoy it. I thank you a lot. And I'm here until you finish, also when it's on Zoom. And I will go on, if you wish, to stay in touch. I'd really like to. And if you wish to hear more about lectures or just, I don't know, like personal letters or something like that, I'd be really glad. And good luck tomorrow. You're welcome.